Greetings everyone, this is Kavita. Today I have decided to take the topic polymers. It's a pretty small topic, but I won't be able to cover this in this video. Hence, this topic is going to be covered in 3 videos, 3 parts at least. Let's get started without wasting much time. And please remember to subscribe to my channel and continue getting new updates by hitting that bell notification. Thank you. So let us understand the meaning of the word polymers. The word polymers is made up of 2 words, poly, which means many, and mers, which means parts, or it also means units. So polymer is basically a big molecule which is made up of many small units, small molecules called as monomers. Now, for example, I can give you protein is a polymer. So what is protein basically? Protein is a macromolecule which is made up of smaller molecules, that is monomers, called as alpha amino acids. So we can call them as monomers. So that was your first example, proteins. Now, let us understand, if I want to hydrolyze proteins by adding acid and water, the ultimate product is going to be the alpha amino acids. So these alpha amino acids are nothing but the monomers. The next example is going to be a synthetic polymer, that is polythene. Polythene is a polymer, that is a macromolecule, and if you see in its name, I can enclose this polyethene, which means many ethene molecules are combined together. So polythene is a polymer which is made up of small molecules known as ethene. So I will call ethene as a monomer. So that was the second example. Now I can take this example as PVC, polyvinyl chloride. So polyvinyl chloride has got vinyl chloride as its monomer. So I can just write down that vinyl chloride is the monomer. So I'm sure you've understood how to understand what is a monomer and a polymer. This is the short form. Let's see the definition of monomer now. Monomer is a simple molecule which is capable of undergoing polymerization. Okay, so it has to be undergoing this process. Polymerization, how do you define it now? So before that, let's see what is an example of this. I'll give you the example ethene. So ethene is a monomer. Vinyl chloride is a monomer. So these molecules are monomers. Now polymerization is a process in which monomers are going to combine to form polymers. Now these monomers can be either only one, so that's called homopolymers. If you have more than one type of monomers, then that is going to be called as a copolymer. So remember this word, copolymers. So example we can write over here. For homopolymers, the best example and the easiest one is polyethene. And in copolymers, I can take 2 examples. First example, which is the simplest one, is nylon 6,6, which was asked in the board exam, also in the 2018 paper. Now let us come back to this flowchart of ours in which we have divided the polymers. So here the first category classification is, we are going to have basically 5 types of classification. The first type is based upon source of origin of polymers. So based upon source of origin, I can have natural polymers. Natural polymers are definitely those which are either occurring in plants' bodies or in animals' bodies. So in all the animals, whatever like protein, for example, is the best example which we can write over here. Yeah, so protein is the first example, and immediately we can write natural rubber also. It's a fantastic example which we can have, or same way nucleic acids also we can have. Rubber is also there. So rubber is also a natural polymer. The second is your synthetic polymers. In synthetic polymers, we have got all those which are widely available here. Man is making all that, so it's man-made. And the example is anything from this chapter of 12th standard polymer chemistry we can write. I've written polythene, which is the simple one to remember. The next is your semi-synthetic. That means you're going to do something on the natural polymers because you're not happy with them, because you want to make them a better polymer to increase their properties. For example, here I have got the first natural polymer. I had used rubber. So in rubber, which is not very good, not very elastic, we are going to extend its elasticity. We are going to make it a better rubber by heating with sulfur in the presence of ZNO. That's going to get converted into vulcanized rubber. So what is vulcanized rubber? Rubber plus sulfur is vulcanized rubber. Coming back to the same chart, we have the second classification based upon structure of polymers. So depending upon the structure, the first is linear. Linear polymers, like for example HDP, high density polythene. The second one is branched. These are the branches, and this is called LDP, low density polythene. The third one is going to be cross linked. Example is bakelite. So these are the three types depending upon whether high density polythene has got linear structure. Because of being linear, the packing is going to be very close, and that's why it's going to be very dense and very tough. Low density polythene has got branching in its polymer chains. They cannot have a very close packing. That means they have got loose packing, and that's why they are low dense. So this is the difference between HDP and LDP. Bakelite. The third example is bakelite. Here we can see it's a heavily three-dimensional network solid, very tough. These are the cross links. The next classification is based upon mode. Now, mode of polymerization means how are you going to react? How are the monomers going to react with each other? Are they going to add or are they going to condense? So based upon that, these are the two types, addition and condensation. Let's see. So addition polymers. In addition polymers, first of all, I'll just try to make two distinguishing features. The first is what are the monomers of addition polymers. The first is unsaturated, and in condensation polymers, they are going to be bifunctional. You must understand this first difference very well. The second difference is that here we do not get any byproducts, no byproducts. Here, definitely there are going to be byproducts. In our syllabus, generally we are seeing that water molecule is the byproduct. Sometimes ammonia gas can come out. Now let's take a fantastic example once again. For addition polymerization, we have taken ethene. You can see I've written N. Small n indicates many molecules of monomers. So this is the molecule of ethene which has got a pi bond. And what is going to happen to this pi bond? We are going to have a free radical mechanism where homolytic fission takes place, and the pi bond breaks like this, and the two electrons go on the left and the right, and this whole thing has to be enclosed in the square bracket, which indicates that this is going to be my repeating unit. So I'm just going to write this in the square bracket, and this entire stuff which is in the square bracket is going to be called as repeating unit. So this can be a 1 mark question in the board exam. What is the repeating unit of a given monomer? So whatever is written in the square bracket. Now this N has to be written here. So this entire structure is going to be called as polymer, that is polythene. So that was your addition, no byproducts. And it's going to be either your low density polythene or high density polythene, depending upon what kind of catalyst have you used, whether you have used oxygen or something else. Now condensation polymers, the first is bifunctional monomers are used and the byproducts are not there. I'm going to take one example now over here. The first example is going to be adipic acid. This is your adipic acid and this is your hexamethylene diamine. So the point to be noted is that both of them contain 6 carbon atoms each. Both are bifunctional. This is your adipic acid. This is, so you can see that both of them contain 6 carbon atoms here. This is having a functional group COOH. This is also having, so what is going to come out from here is OH, and from here I'm going to knock out the hydrogen atom. Condensation takes place. Same way from the left hand side I'm going to knock out the OH, and from here I'm going to knock out the H. So what answer it looks like is, if I write it down, I'll have to remove this OH and write the structure as C double bond O, and this entire thing will have to be rewritten, and this OH has gone. So I get a new bond over here, NH. So that's your new bond, that's amide bond. and the entire thing as it is. And remember, from that last side also I have to remove one H, and now I have to write the N. So that's your repeating unit, and this is going to be my n number of times, so plus 2n minus 1 water. So this is going to be, so that's your byproduct. Water is coming out over here in the condensation polymerization. The name of this famous polymer is nylon 6,6. This year in the board the question was asked why it's called 6,6. The reason is because both the monomers have 6 carbon atoms each. Now let's go to the fourth one, molecular forces. So based upon molecular forces, I can divide the polymers into 4 different types. Let's see what are those. Based upon the intermolecular forces of attraction between the polymers. So the first one over here is known as elastomers. So these are the elastomers. They are going to be like elastic. Based upon their van der Waals forces of attraction, we are going to divide them like this. The weakest one is going to be your elastomers, and the strongest ones are going to be the thermosetting polymers. The forces are going to increase in the order downwards. The first is elastomers. The second one is going to be your thermoplastics. That means plastic, polythene, everything which is recyclable. Then you have your fibers, which are going to be thread-like, and finally we have thermosetting polymers. Alright, so let's see the first one now. So in this manner you have understood there are 4 types: elastomers, thermoplastics, fibers, and thermosetting. The first one now I'll just talk about is what happens in their van der Waals forces. The first, elastomers will have the weakest intermolecular forces of attraction, because of which they can be stretched and they can regain their shape back once again. We can introduce crosslinks over here by adding sulfur crosslinkages also, like for example in the case of rubber. The example of this category, if you can just write down here, is rubber. Vulcanized rubber also will come into this category along with Buna S, Buna N. All these are your elastomers because they can be stretched. So they have weak forces of attraction. So even this also I can write here. Okay, so now the thermoplastics ones, as the name suggests, they are going to be, having polythene is the best example over here. We can have polyacrylonitrile, and this is the full form PAN. This is polyacrylonitrile. It is going to be having a little stronger intermolecular forces of attraction than fibers. As you can see, they are having very good strong bonds. That is, hydrogen bonding is the most important, and they are going to have a very close packing, and because of this close packing they become very beautiful crystals. They have got crystalline appearance, and they have got very high and quite sharp melting points rather. Example is your nylon 6,6, nylon 6, your dacron, terylene, etc. The last category is your thermosetting polymers, which have got the highest, strongest intermolecular forces of attraction. The example over there here is bakelite. They have a 3-dimensional network, and they are very tough and rigid. They cannot be softened once they set. So they are going to be infusible masses once they are setting. So they cannot be reused, recycled. So that was your 4 types of polymers. Now we'll go to the next category after this. So these were the ones. The last, growth polymerization is the last one. Now in growth polymerization you can have 2 types. The first one is going to be your chain growth polymerization, which means the chain is going to become bigger and bigger. The step growth polymerization is the one in which different types of functional groups are obtained. Let's go to the first one. It's also called addition, and this one is also called as condensation polymerization. I'm going to take one fantastic example once again, that is polythene. Okay, so in polythene, let's see the mechanism which can be asked at the board exam for 2 marks. Chain initiation is the first step. Now what happens in this step? You have to take an organic peroxide which acts like an initiator. Benzoyl peroxide is the initiator over here I'm going to use. Okay, so that's your initiator. What happens to this initiator? Now when I bombard light of suitable frequency on it, or I heat this compound, it automatically undergoes homolytic fission in this fashion. Okay, and we get two radicals. These radicals are going to be called as benzoyl radicals. They are not very stable, so definitely they are also going to break down. This is my benzoyl radical. It will break down to give me phenyl radical. You can see that this electron goes here. Okay, this one also undergoes homolytic fission. It gets settled over here, and these two combine and we get pi bond over there. The resultant is two phenyl radicals and carbon dioxide gas. So two phenyl radicals are going to be formed here. Let's write its name here. So that was the first step. Now what happens to this radical? This phenyl radical is going to be now attacking this phenyl radical attacks the CH2 double bond CH2, and you get monomer, and it attacks over here, and the same thing goes, and this kind of mechanism can be shown. Actually this can be shown in the first step only. It's called chain initiation because now the chain has started forming. So this step actually can be shown in the chain initiation only from here. And now the chain propagation starts over here actually when I'm writing this. So this is your chain propagation where the radicals are going to become longer and longer due to the attacks. This is your big radical. Now this big radical is going to combine with itself, and this is the whole thing which I have written in the bracket, which indicates that the length is going to increase. So that's why it's called chain growth. The last step is going to be a chain termination. So in chain termination, you're finally going to stop the growth of the chain when two such radicals combine together and they form a big molecule that's called as polythene. So what we are going to do now is going to write the same structure once again, two times. So that's your CH2 dot radical plus one more of this type. We can write like this. So as you can see that two such radicals are very close together. They have one electron each. They can just combine and make a covalent bond. And the structure I can just write out here: pH CH2 CH2 n number of times CH2 CH2, and that second one also I can write it and show it to you, the whole structure this way. And see, now the electrons are going to just join up. So that's your polythene. Now the chain growth, what we learned, it's going to give you length, increase in the length. Okay, and now let's see what's going to happen in the step growth. In step growth polymerization, we are going to see a good example once again. In each step, a distinct bifunctional species is formed. So you'll have a different types of functional groups on either side of the chain. The example I'm going to take is these two, the same example: hexamethylene diamine plus adipic acid. When they combine together for the first time, you can see that there is an amide linkage formed over here. These two people have, OH and NH have gone out, and the same structure if I write on the left side, the NH2, same way NH2 is still there, and on this side I write CO, CH2 4 times, COOH. So here what is there? COH is there. So the first molecule dimer which is formed has got two different functional groups. One is COH on the left and one is NH2 on the right. Now what happens that if this COH combines with some other NH2 on the right side, what happens? So we can just write it this way. And on this side I've got NH2, but on the right side this COH has combined with another NH2 on the right side, and this is a trimer which is going to be formed. You can see what's happened. Such a big molecule which is called as trimer is formed, and on both the sides of the trimer you can see that there are different functional groups. NH2 is there on the left, NH2 is on the right, but on the dimer, what was there on the dimer? It was NH2 on the left and COH on the right. So every step will have a different type of functional group in the case of step growth polymerization. That's all from this video, and in the next video I'll cover up the next topics which I have not taken yet. Subscribe to my channel and keep watching the new things